All right, so we start our let's talk for this morning section with Benjamin Gammage from Harvard University.
At the University of Toronto, actually.
University of Toronto.
So thank you for inviting me. I'm very glad to be back here. I've been here a while at the start of my postdoc, and very nice to be here, especially on a day when Toronto is having its first snowstorm of the season. So I didn't get a chance somehow to give a title or abstract for the website. So I'll give a title for my talk as so I think this conference is titled New Developments in Singularity Theory. So I'll call this talk New Development in Perverse Chauffeurs. So yeah, I wasn't sure sort of exactly what to talk about. I don't know if the singularity theory is exactly the main thing that I've been thinking about recently, but I've decided that I have been thinking a lot about these things, and I think they do relate to singularity theory in a lot of interesting ways. And basically, I just like to tell you about them. So I think much of the what I'm going to say, most of what I'm going to say is not really original to me. I'm just going to sort of do a summary of a lot of developments in this field, and hopefully how it relates to various questions that I think people in this room might be interested in. So as usual in my talk, don't really have a place where I'm trying to go. So you can, this talk even more than usual, so you can feel free to interrupt me at any time and ask for more explanation or ask for me to go in a different direction. But maybe I'll just sort of start with a little motivation of what this thing is. So if I have a Kähler manifold, and I have a function on it whose, let's say for the moment that this function has only one critical value at 0. If it has any critical value, you can shrink down to a small disk here and to get to that local situation. So I'll start by sort of talking about that local situation, and you can ask the question of kind of how do we measure the change in the fiber of this function. I'll call it xt as t goes to 0. So there's various things you could try to do. I think that sort of classically, one thing you might do is you might kind of look at the cohomology and ask, how does the cohomology of the fiber, how does the cohomology of the general fiber relate to the cohomology of the special fiber? So, one way to summarize that is you can define a sheaf, which is the push forward of the constant sheaf with coefficients k on x along this map path. So then this is going to be a perverse sheaf. Maybe if you shift it enough, this will give you a perverse sheaf on C with singularity at 0. Okay, so what that means is that this is a sheaf that this is something that away from 0 is a local system on C, right? Because x has only critical value 0, so it's a fibration away from 0. So kind of you have a fiber bundle away from 0. So the cohomologies form a local system. They're locally constant, but have a monotone as you go around 0. And then something interesting happens at 0. Sort of this word perverse is meant to signal that like we have a good understanding of the collection of all perverse sheaves and how to describe their invariance. And so there's this classical calculation. I'm never sure who to attribute this to. It's due to a lot of people, I'm sure. But there's this classical calculation of what is the category of perverse sheaves on C with singularity at 0. In other words, what data characterizes such a thing? And it turns out that you can characterize these things in terms of linear algebraic data. So there's a pair of vector spaces. This psi is traditionally called the nearby cycles of the sheaf, right? So this thing is like, epsilon. It's the stalk of your sheaf at epsilon, like away from 0. So this is, in other words, the cohomology of a general fiber here. This is the nearby cycles. And it comes equipped with a monodromy automorphism. I'll call this T. So this T is a monodromy automorphism that again makes this thing into a local system over C star. So that's what I just said. But like if I look at what's happening away from zero, then I get the cohomology of my general fiber, and it has this monodromy automorphism. But then it turns out that the data of one of these things that encapsulates what's happening at zero also has another vector space called phi. This is the nearby cycle. This is the vanishing cycles. So there's various ways that people describe vanishing cycles. I mean, classically, this is literally like if you have a Lefschetz vibration, the nearby fiber has some sphere in it that like gets crushed to zero as you move to zero. And this is the vector space spanned by those. You can also, in terms of the cohomology of this perverse sheaf, think of it as the sort of sections of the sheaf that are supported along the positive real axis. So the non-negative real axis. So this is the vanishing cycles. It also, it turns out, has a sort of monodromy automorphism on it. And then there's a canonical map from here to here. So another way of thinking about the vanishing cycles, I'll just say this here, B can also be understood as the cone on a map from the global sections of F to the nearby fiber. So in other words, this phi fits into an exact triangle with, I have the global sections of my sheaf, that's everything that extends over the whole space. Then I have the stuff that's just on the nearby fiber, and this phi is measuring the difference between them. It's the third term in this exact triangle. So from that, I get a canonical map from here to here. This is usually called the canonical map, and maybe I'll leave it as an exercise that there's also a variation map going the other way. So I'm calling these X and Y, and these satisfy some relations. And they're that the composition of X and Y is equal to one, the difference between the identity and the monodromy. So I'll write 1 minus xy is equal to the monodromy on phi, and 1 minus yx is equal to the monodromy on psi. Okay. So this was some classical computation, and it says basically that if you have, if you're in this situation where you're sort of where your x is sort of locally constant away from zero, and you study the cohomologies, and you want to know like how can I encapsulate all the data of the cohomologies and the various restrictions among them, all of that data is encapsulated in terms of this linear algebraic thing. Any? Yeah, I mean, okay, I should probably put some. I mean, I don't want any singularities to happen at infinity here. But so if I assume that there's no singularities in infinity and that this is all that's happening, then this will be tell me everything. I mean, this is putting that aside, this is a theorem that the perverse sheaves on here on this thing are encapsulated by this guy. And so maybe this top part is sort of motivation of like, where do you get a perverse sheaf on here? And yeah, maybe I should have required that X be proper in order to ensure that I do get this perverse sheaf. Any questions about this calculation? Again, if you haven't seen it before, it's a great calculation. So I think I've already said this, but let me just write it down, that this vector space psi, together with the automorphism T on it, is a local system on C star. Maybe okay, I'll maybe leave that there for now, and I'll come back to that discussion in a moment. Okay, so this was nice. This is one thing you could do, but of course the cohomology is a rather weak invariant. So like if I'm only looking at the cohomologies of the fibers, I'm only going to see so much. And so my sort of for the past several years, I've been going around trying to evangelize to everyone that we want to categorify things. That like it's better sort of to think one categorical level up, and you get much richer invariants. So a better thing that you can do, and so this idea originally goes back to, I'll attribute this idea to Kaprano Shachman, which is that you can study, maybe, I don't know if they conceived it in these terms when they were first defining this, but instead of studying the sheaf whose stalk is the cohomology of the fiber, you should study sheaf whose stalk is the Fukaya category of the fiber. Okay, so now you can say that, okay, I get sort of like a Fukaya category of each fiber. I have this local system of Fukaya categories. So this is some sort of, invariant of the symplectic geometry of these symplectic manifolds, which are the fibers of this map. And you can ask, like, how do those invariants behave as I acquire a singularity at 0? And so they define something that they call perverse Schober's. I'll maybe call this perverse sheaves of categories. That's kind of what Schober means. It just means sheaf of categories. So what is a perverse sheaf of categories? So one way to figure it out is you can sort of stare at this picture and see what would happen if you replaced your vector spaces with categories. So a perverse sheaf of categories is the data of, so I'm going to start with a category. I'll call these two categories C phi and C psi. So I should have, instead of a pair of vector spaces, a pair of categories. Each one of them should have an automorphism. I'll call these automorphisms T, as before. T is my automorphism on here. And then instead of a linear map between vector spaces, I should have a functor between categories. And then I note to myself, well, what's the meaning categorically of saying that, like, now, I have some equation here of linear maps that says that, 1 minus xy is equal to t. So I want to have some equation like 1 minus fg is equal to t. But, where do I get like a minus of between functors? And I noticed that in categories, I actually can have natural transformations between functors. So instead of 1 minus xy, I'm going to have a map from the identity to fg. And if I think about where do maps from the identity to a composition of two functors, or from a composition of two functors to the identity come from, they come from when these two functors are adjoint to each other. So if you have a pair of adjoint functors, then it makes sense to talk about the unit or co-unit map of the adjunction. So what I can do is I can require that if I have the unit map of the adjunction, so I have the identity on C phi, this thing has a unit map that goes to the composition GF, and I can require that that thing sits in an exact triangle with T phi. And I can do the same thing on the other side, that I have a co-unit map from the composition FG to the identity on C psi, and I can require that that sits in an exact triangle with T psi. Exact triangles. Okay. So in other words, what this is saying is that I have this this pair of categories and an adjunction between them. Moreover, I have some feature of the adjunction, which is that the unit map is somehow encoding this monotropy. That, like, given the unit map of an adjunction, you can always ask, well, okay, what's the fiber of that map? What's the thing that fits in here? Or what's the cone, the co-fiber of this co-unit map? It's the co-unit of the adjunction. I can always get these two other things by fitting them into these exact triangles. But in general, these things will not be automorphisms. So that's the special feature of this situation is that the third term in these exact triangles is in each case required to be an automorphism. So this is a two category that goes by a special name besides perverse Schober. Sorry, I should have written here. This was supposed to be perverse sheaves of categories on C with a singularity of 0, like before. And this two category also has another name. These things are called spherical adjunctions. Or F and G are also called spherical functors. So this goes back to the work of Rina Ono, later enhanced in work of her with Timothy Logvinenko. This comes from the fact that if you take one of your categories to be just the category of vector spaces, then a functor from vector spaces to something else just picks out an object. And if that object is like the vanishing sphere in a Fukaya category, then you're going to find that this this sort of whole business here just comes from thinking about the cohomology of a sphere. And those were what were called spherical objects. So that's where that terminology came from. Okay, so I've defined you some, this is actually a two category, although let's not let that worry us too much. I've defined some enhancements of the usual category of perverse sheaves. So kind of the purpose of this talk, and a lot of my talks, is just to kind of encourage people that this is a really rich invariant to study that tells us about how things change as you know, how maybe a Kähler manifold changes as t goes to 0. Any questions about this definition?
So C phi and 6 psi should be Fukaya categories of
So yeah, so right. So in this sort of model setup, C phi, so maybe the example is that in this setup here, I could have my spherical adjunction would be that C psi, the sort of nearby category. So that would be the Fukaya category of a nearby fiber, like Fukaya category of like X at the fiber 1. And then this C phi, the vanishing category, is actually going to be category 1. And then this C psi is going to be the Fukaya-sidal category of the total space with superpotential M. So kind of this Fukaya-sidal category is exactly something that is supposed to sort of, it's supposed to kind of categorify vanishing cycles, and it's sort of measuring, again, it's measuring something about the critical values of this function. And then given the measuring the critical values of the function f, you can also ask, what if I restrict to f inverse of 1 and just look at that Fukaya category? And so there's these classical Orlov or Kapp functors that go between these. And these, I think Zach Sylvan was maybe the first one to prove in general that these form under some very mild hypotheses a spherical adjunction. So that's how these things arise in symplectic geometry.
the phi and psi are twisted here, but here the
well, yeah, I mean, the situation is sort of symmetrical.
Okay.
The situation is sort of symmetrical. I like to write this one this way and this one this way, but maybe I don't have a good reason for it. Or maybe I do have good reasons, but it's hard to. There's also kind of a Fourier transform switching. I'll maybe say some more words about that a little bit later. But you can notice that both of these descriptions are totally symmetrical in phi and psi. Which is interesting because obviously this does not look very symmetrical. I mean, this also didn't really look very symmetrical. The one of them was measuring the nearby fiber. One of them was mentioning this vanishing stuff. Maybe I'll just draw a picture that if I take the 0 section union the co-normal to 0 inside of T star C. This looks like this looks a little bit like this. It looks like sort of two copies of the complex line meeting at a single point. And I can think that kind of psi is measuring, if I have something that's sort of supported along these things, psi is kind of measuring its stock right here, and phi is kind of measuring its micro-local stock up here. But if I have a sheaf on C, there's this micro-local picture of geometry where you can measure not only its stocks, but also its kind of micro-local stocks where it has a singular support. And you can see that this picture is sort of, I mean, these two sides look kind of the same. If you tilt your head 90 degrees, then they look similar. So, yes. Any other questions about this definition? I'm saying a boot now because I'm Canadian. I've been working on that when I teach my class. It's a struggle. I'm still saying Z, so that's going to take a long time to relearn. Okay, so let me repeat this remark here, but over here. So let me note that this C psi now with automorphism T is a local system of categories. So it is a local system. I mean, a local system of anything on C star is like that thing together with an automorphism, right? Because C star is a K pi 1. So this is a local system of categories on C star. And it is sort of categorifying this thing here. So in other words, it's categorifying the monodromy of the Gauss-Manin connection. Monodromy of the Gauss-Manin connection on the cohomology of a fiber. I'll switch markers this way. Yeah, so that's kind of an interesting thing. So let me point out that this, even if I just restrict to C psi, if I know that C psi was the if I know that C psi is the domain of a spherical functor, it comes with some extra structure, but C psi with this automorphism T also has extra structure, namely, so again, this is part of the sort of two categorical richness that you didn't see before. Previously, if I sort of looked at this picture in the one categorical setting, and I said, well, okay, if I don't know about the vanishing cycle space, if I only know about the nearby cycle space, what do I know about it? All I really know about it is that it has this monodromy T on it. Right, I had this other equation, 1 minus xy is equal to t, which means that knowing t is the same as knowing xy. It's like the composition of xy and t were just equivalent pieces of data. But in this case, of course, knowing t and knowing gf are not, or knowing maybe t and knowing fg are not equivalent pieces of data. There's a map between them. Or maybe if I, there's an exact triangle among these with the identity. So this has extra structure, namely a map from the identity on C psi to T. Sorry, I know I keep going back and forth between signs, but let me do this with phi instead. I think I like that a little better. So it's sort of symmetrical. So C phi also has extra structure, namely, in this case, the map goes the other way. A map from T to the identity on C phi. So this is one extra piece of structure that you didn't see here, right? Because this thing sort of decategorifies to a minus sign. This map satisfies some, maybe I should say such that such that if I complete this to an exact triangle, so if I take the cone on this map, then the third term in the exact triangle is an exact triangle where M is a monad on C phi. Right, this is the structure of adjoint functors, is that if you compose two adjoint functors, you get a monad, which is this monad GF. And if I had done C psi, then I would have gotten a comonad, FG instead. So it would be a similar story, but I would say comonad instead of monad. So let me give a definition, to just formalize what I just said. So a monad, M, on a category C is spherical if the unit map fits into if the fiber of the unit map is an automorphism. If the fiber of this unit map from the identity, so whatever a monad is, it's something, it's an algebra object in endofunctors of C. So it's something that has a multiplication, has a unit map coming from the identity. So the fiber is going to be if I have this here, the fiber is going to be the thing, the third term in this exact triangle. And I can require that functor, so that thing is going to be some endofunctor on C, right? Each of these things is an object of functors on C. This is an object of endofunctors of C. And I can require that thing be an isomorphism, be an automorphism of C. So this is a functor from C to C, and I can require that this thing is an automorphism. Okay, so that's what a spherical monad is. So the reason why I've introduced this definition is that I want to sort of, again, try and motivate this a little bit with reference to this. So if I have a local system, if I have a local system on C star, right, which I said that if I restrict it to the C star, then I just get a local system. And given a local system of things on C star, so okay, I have an embedding. Maybe I'll just write this here. J is going to be the embedding of C star into C. Using the embedding of C star into C, I can push forward any local system on C star, and then I'm going to get a perverse sheaf on C with singularities at 0. Maybe I should just say a sheaf with singularities at 0. Whatever, I don't want to be too worried about T structures and things here, but you know, roughly speaking, if I start with something here, there's oh, sorry, I did this wrong. Yeah, I did this wrong. Sorry. If I started, the thing I said before was that if I had a perverse sheaf on C, I could pull it back to C star and then get a local system, and then get a local system on C star. And now the point I wanted to make is that this functor actually has both a left and a right adjoint. So the left adjoint is called the proper push forward, and the right adjoint is the usual push forward. So in other words, this tells me that like given a perverse sheaf, I can restrict it to C star, and then there's two ways of kind of freely or kind of co-freely inducing one of these objects, just starting from this data right here. And so I want to make the point that this is categorified by so now I can do something similar, but I can start with a spherical monad. And then if I have a perverse sheaf of categories on C, so we've just seen that I have this kind of restriction map. So maybe I'll give it the same name, J upper star, which is if I have a perverse Schober on C, then as I said, I can restrict it to just thinking about one of these things. Then I get a category with nautomorphism and a map from the unit from that automorphism fitting into an exact triangle with the monad. So I get a spherical monad or a spherical comonad, depending on my conventions. And then there's also, this map has both a left and a right adjoint. And these are actually very familiar. If you can ask, if I have a monad, how do I extend it to an adjunction? And if you ask a category theorist this, they'll tell you, well, like, given a monad, there's a canonical way to make an adjunction. It's called the Eilenberg-Mohr construction. But there's also another way to do it, which is the free way of making this is like the category of, you know, this is given a monad, you can look at the category of algebras for that monad, and that has a natural adjunction with your original category. Or you can look at the category of free algebras for that monad, which is called the Kleisli construction. So the Kleisli construction and the Eilenberg-Mohr construction of algebras for a monad or free algebras for a monad are really, you should think of them if you knew what they were before, now you have a geometric way of thinking about them. And if you didn't know what they were before, you could think to yourself, okay, this is some higher categorical version of taking something on C star and either star pushing it forward or sheaf pushing it forward. So I think that's very nice. And I'd like to develop this idea a little more. Let me pause now and ask if there's any questions about what I've been saying here.
The monad is decomposed F.
Yes. Yes. So my monad here was decomposed F. And the point is that, like, if I just looked at one of these two categories, now I've forgotten about the functors F and G individually, but I can remember their composition. And previously, that didn't give me any extra information remembering X, Y, because it was just equal to 1 minus T. But here, remembering GF was more information than just remembering T, because they fit into this exact triangle. There were the two morphisms. The theme of this talk is that, like, two morphisms can tell us some extra rich structure about what's happening. So let me ask a question now, and then I'm going to answer it. Maybe first I should motivate it. Unfortunately, going to erase my perverse sheaf diagram. We have the perverse Schober one on the board.
I also recalling the automorphism.
Yes. That's what spherical monad is doing. So I said a monad is spherical. I mean, if I have a spherical monad, then T is the fiber of the unit. So the point is that, like, it's encoded in the unit map of this. And the way I phrased it this way is that actually saying that T is the fiber of this thing is much stronger than saying that C just has an automorphism with a map to the identity. It actually ends up being that T is what's called a well-pointed automorphism, which means that like a priori there's two different maps from T squared to T using the unit map on one or the unit map on the other, and those are forced to agree by this by the unit condition of the monad. Any other questions? So okay, I'm not going to get as far as I wanted in this talk, but that's good. I feel like I'm already going too fast. Normally, sort of when I give a talk, I sort of spend most of the talk talking about 3D mirror symmetry or relative Langhans or something, and then I introduce this thing in the last 5 minutes of the talk, and no one understands. So I'm hoping that by introducing this earlier in the talk, we get some chance to learn some things about it. So a question that I might want to ask now is, okay, so we had this example that perverse Schober's naturally arose in symplectic geometry. But I might also want to ask, how do perverse Schober's arise in algebraic geometry? What I mean by that is that, where is a source of getting a perverse Schober where these categories are not like Fukaya categories of something, which maybe some people like, some people don't like, but can I get a version where these categories are categories of, the derived category of coherent sheaves on an algebraic variety? So that's a category that, as we know, has a lot of rich information about the algebraic geometry of an algebraic variety, and can we also sort of fit that into our perverse Schober story? And maybe some motivation for this question. Maybe before I proceed, let me just give some motivation, which is that there's an expectation, which is that if X is a Kähler manifold, then what you should get is that coherent sheaves on X is part of a perverse Schober over its extended Kähler moduli space. Maybe I'll just say over its stringy Kähler moduli space. So stringy here means both extended, something about that in a second, and complexified. Right, so if I have an algebraic variety, oftentimes it's sort of birational to other algebraic varieties. Maybe it's birational in a nice way. It's even like K equivalent, and then it's actually its derived category is that it's also derived equivalent. And you can ask, like, where do those derived equivalences between different algebraic varieties come from geometrically? And we've seen that, like in this case, let me just kind of draw a picture. Here's a picture of C. I have a singularity at 0. And in algebraic geometry, I'm used to only considering a real Kähler moduli space of a variety. So if I have a variety where, like, as I vary the Kähler form, maybe I'm varying the Kähler form over this real line, and nothing is happening, like I have a T star P1, and the P1 is sort of getting smaller and smaller until it collapses and acquires a singularity at this point. And then maybe I can grow it out in a sort of anti-holomorphic way in the other direction or something. And the point is that, like, in this stringy Kähler moduli space, these things that looked like walls, real codimension 1 walls in a real moduli space, actually are real codimension 2 in a complexified version of the moduli space. So there's actually kind of monodromy automorphisms taking you around from here to here. So, if you really understood how perverse Schobers arose in algebraic geometry, you might understand a lot about birational equivalences of algebraic varieties. Or when those things give you derived equivalences, or how the derived equivalences are related to geometry. So that's some kind of general.
Part of this data, and like the reason you can complexify, is that you're tracking some sort of bridge stability condition around. Is
that would be, yeah. So that's the way that you could try and make this more precise. Yeah. Exactly so. Like the problem, of course, is that that's like too difficult in general, because like we don't know a lot about the great stability conditions. Yes. But like we have this dream that like maybe I do know about bridgeland stability conditions, and then yes, I follow a bridgeland stability condition, and that's where my kind of monodromy is coming from. And then maybe kind of even I can like degenerate my stability condition, and that involves the degeneration of my variety, and that involves like this kind of other category here. And something nice about this perverse Schober picture is you see that like I'll maybe give a different presentation of these perverse Schobers in a bit, but like you see that like just from this these two categories and the functors between them, the monodromy pops out automatically. Like if you knew this like the nearby category, which is coherent sheaves on X, and you knew coherent sheaves on the vanishing category in an appropriate way, then like the functors, the adjoint functors between them automatically would give you this sort of monodromy on the nearby category. So yeah, so this is a very nice picture, and just and it's sort of mirror to this other picture I said where like perverse Schobers here we're categorifying monodromy of the Gauss-Manin connection. Here they're sort of categorifying monodromy of the quantum connection on an algebraic variety, because the quantum connection is sort of insensitive to the complex structure, but it has some monodromy there. Okay, so this is some dream, and this underlies a lot of conjectures in the subject. So let me kind of try and give a partial answer to this question. So this is an answer that I arrived at with Aaron Maisel G and Justin Hilburn. And maybe I won't state our theorem precisely, but I'll say imprecisely that the answer to this question, how do perverse Schobers arise in algebraic geometry, is they come from the data of an algebraic variety Y together with a map to the Arden stack C mod C star. So maybe I'll state part of the, okay, well, let me sort of state part of our theorem precisely, and then say a little bit more about what a map from Y to C mod C star is. So here's a theorem, which is that spherical monads. So there's some two category of spherical monads here. A category equipped with a monad satisfying this condition that the fiber of the unit map is an automorphism. And the theorem is that a spherical monad, so like I said before, that like over here I saw some things like this thing with this category with just the automorphism here is like a local system of categories on C star. I can do something similar. A spherical monad, so that's the data of a category, not just an automorphism, but an automorphism that arises in an exact triangle with the unit map of a monad. This is equivalent to the two category of quasi-coherent sheaves of categories on C mod C star. So okay, this is some two category that maybe you haven't seen before. Let me put this in a slightly more one categorical way. Whatever this two category is, it's equivalent to the two category of module categories for a certain monoidal category, namely quasi-coherent sheaves on C mod C star. Okay, so the category of quasi-coherent sheaves on C mod C star, this is some algebraic object. It's a stack, but okay, it's not a very bad stack, whatever. It's some algebraic object. It has a category of quasi-coherent sheaves. I can tensor two of them. That makes this into a monoidal category. And so I can look at the modules for that monoidal category in categories, right? So a category with an action of this monoidal category is the same data as a spherical monad. So kind of, if you were trying to build all the perverse Schobers, you'd see that like your first step is to build the spherical monads and then kind of push them forward and kind of know I've told you that spherical monads in algebraic geometry are exactly the same thing as like they come from a variety with a map to or a stack, whatever, with a map to C mod C star. And just to complete this discussion, let me say that what is a map from Y to C mod C star? Y is some algebraic object, some algebraic variety or algebraic stack or Taylor manifold, whatever you like. And I'm going to tell you what it means to map it into this step C mod C star right now.
What's the connection between Y and X in general question? I mean, philosophically, not.
Yeah, not maybe there's no difference. I just didn't want to use the same letter in case I might have some I might be like this category current chiefs or X might be playing like the role of one of these categories. I was just trying. It's the same kind of thing as X.
I thought that X is the fiber. Yeah, X is the fiber, isn't it?
Well, why? Let me write a couple of more things down, and then people can re-ask me this question. Let me just say the way I think about a map from Y to C mod C star, which is a map from Y to B C star. If I just had instead of C mod C star, if I had point mod C star, so point mod C star B C star. Okay, I think we all know that a map from anything to BC star had better be a line bundle on that thing, right? BC star is the classifying space of line bundles. So map from Y to B to C mod C star. Well, first of all, it's going to be the data of a line bundle L on Y, and then I can ask, well, what about this extra that Y is actually mapping to C mod C star? And the fact that C has weight 1 for the C star action is telling you that like this map here becomes a section of this line bundle. So this is the data of a line bundle L on Y plus a section, which I'm calling S, of the line bundle. And that data is the same thing as if I have a line bundle with a section, that's essentially the same data as a divisor on X on Y. Divisor D, which is of course X inverse of 0 inside of Y. So this is the space of some kind of space of Cartier divisors on Y. And in that case, maybe I'll keep my definition of Schober's up on the board. But so in this case, this gives you a spherical junction between coherent sheaves on Y and coherent sheaves on the divisor, where these maps are the pullback and push forward map respectively. So just like in symplectic geometry, sort of universally, Schober's on C came from the data of a map to C together with came from the data of a map to C, and this was the Schober, was the Fukaya category, the fiber, and the Fukaya-Seidel category of the superpotential. Schober's from algebraic geometry perspective come from map to C mod C star. And kind of every sort of Schober that arises in algebraic geometry in some sense like is supposed to come from something like this. You should think of like whatever Schober is from the algebraic perspective, it's like this two categories like a non-commutative version of like the push forward pullback of including a divisor into an algebraic variety. So this Y it's somewhat asymmetrical, the construction on the Fukaya side versus the algebraic side. But here Y is of course the sort of pullback of the whole thing, and this Y0 is kind of the pullback of 0. Whereas you could ask for like what's the pullback over point C star mod C star in here, and that would be Y minus T. And that's that plays an interesting role in here as well, and trying to phrase that in this story as well. And I think that's an interesting thing to do. Okay. So yes, that's where Schober's come from in algebraic geometry. And kind of that's our theorem is a little bit stronger than that, but that's sort of part of the content of this theorem.
Before you erase, and you also the groups category for C number 0, you also write that number for C for your category.
Yeah, so that was what I was trying not to avoid by not stating this theorem precisely. But the precise statement of our theorem. So our theorem our theorem told you that this was the same thing as quasi-coherent sheaves of categories on C mod C star. And then you can ask what's this thing here? And the answer is that it's something called incoherent sheaves of categories on C mod C star. So this is something that's like a little bit bigger than quasi-coherent sheaves of categories on C mod C star. This is something that arose in the work of Enrique and also Stefanich. So Stefanich's thesis defines quasi-coherent sheaves of categories and higher categories for all levels. And his work in progress defines, I think, incoherent sheaves of categories. Maybe it already, there's some sort of work about categorification of sheaf theory that defines this. There's also some lectures of Arinkin from earlier where he gives a different construction of what this thing is. But this does have a name in algebraic geometry. And so the actual sort of more formal statement of our theorem is this equivalence here, that perverse sheaves of categories on C is the same thing as incoherent sheaves of categories on C mod C star. Okay. So that's the slogan, is that in algebraic geometry, sort of perverse Schober's look like this. Let me give a alternative presentation of perverse Schober's now. Okay. Do I go until 12:30? Okay. So I could give an alternative presentation of perverse Schober's, or I could maybe I'll give a alternative presentation of perverse Schober's. Perverse sheaves of categories on C0. So there's this alternative presentation of perverse sheaves of categories in terms of spherical pairs. And so spherical pairs sort of fit a little better into maybe this picture that I sketched before. So a spherical pair is, so what is it? I have some category E, and then I'm supposed to have two subcategories of that, which I'll call E minus and E plus. And I want this E minus and E plus to be admissible subcategories. So what does admissible mean? It means that this inclusion has both a left adjoint and a right adjoint. So if I call this inclusion, maybe I'll call this one, I'll call this inclusion I upper star. So I have an I minus upper star and an I plus upper star. And if I write it that way, then I should have its left adjoint should properly be called I minus lower, sorry, no, I write this wrong for myself. I think I must have wanted this to be lower star, sorry. That would make more sense. So I have my I plus lower, my I minus lower star, and my I plus lower star are these things, and then I have its left adjoint is naturally going to be called I minus sorry, let me just call this I minus. Let me, I've got my notation all messed up. I'm going to call this one I minus and this one I plus, and then I'm going to call its adjoint here a I minus upper star and an I plus upper star, whatever. It's going to have some adjoints, and then I can also form the left orthogonals of these categories inside of E. Right, so given an admissible subcategory, it has a left orthogonal inside of E. So each one of those embed inside of here. Let me call these embeddings J minus and J plus. And then I can also define an adjoint to that called J. I'll call this one, the adjoint should go this way, J minus upper shriek, and J plus upper Schrieb. And then the condition is going to be that basically if I go along these functors like this, so okay, so spherical pairs is a pair of admissible subcategories such that so the rule is that if I go from E minus to E plus in the obvious way, so I first go to E this way, and then I take the and then I take this adjoint functor this way, that should be an equivalence. So if I do I plus upper star I minus, and if I do it the other way, so if I start with I plus and then I do I minus upper star I plus are equivalences. And then the second condition is going to be something else here, that the similar thing over here, that if I start with E minus and I go by doing J minus and then this adjoint, then that should also be an equivalence. So J minus upper Schrieb, J minus, and sorry, J plus, no. J minus upper Schrieb, J plus, and J plus upper Schrieb, J minus are equivalences. Okay, sorry, that took a minute. So why is this definition nice? Basically, this definition sort of fits better into this picture here, where like you can imagine that like E plus and E minus. So imagine E minus, E plus. So basically, often in algebraic geometry, we care about kind of derived categories of things that sit on different sides of some wall in the sort of real Taylor moduli space. So you imagine that maybe something like E minus and E plus are coherent sheaves on X minus, coherent sheaves on X plus, where these are two varieties that are related by a flaw. So, you know, there's this K equivalence conjecture that says that kind of if you have a pair of varieties and you have a birational root between them, so the pullbacks of the canonical classes are equal, then there should be a derived equivalence between them. And in general, it's not really known how to do that. And the point is that if you could fit these guys into a perverse Schober like this, into this structure of spherical pair, then you could sort of automatically have this sort of half monodromy equivalence. So these are the kind of, you know, half monodromies, which are connecting kind of like these arrows here, connecting like what's happening on one side and the other side of a wall here. So in certain cases, in some cases, so I'll say there's a very nice paper of Agnieszka Bodzenta and Blondal doing this in the case of certain nice flops of like Gorenstein manifolds where the fibers are of dimension at most one of the contraction, whatever. There's some like hypotheses on the on what's happening here. This is realized. In algebraic geometry, I'll say that there's a lot of papers. There's some papers of Helper and Leissner. There's a paper of Helper and Leissner Sam and Helper and Leissner Shipman, where they sort of also sort of construct some of these kind of spherical pair structures using some sort of window equivalences. Okay, so where am I going with this? So I basically stated a puzzle for you, which is like, given, you know, some flop or birational equivalence or derived equivalence that you have in algebraic geometry, kind of how do you construct one of these spherical pairs? Let me just ask an even simpler question of sort of like, how do these arise in algebraic geometry? Sort of along the same lines of this question I asked before, where I said that kind of like, oh, I found out that the kind of universal structure of one of these spherical adjunctions was like had to do with coherent sheaves of categories on C mod C star. And basically what's happening here is that E, maybe just to explain the relation here a little more between this picture and this picture, that E plus and E minus play the role of, one of these two categories here, maybe like C psi, and that they're left orthogonal, E plus left orthogonal, E minus left orthogonal, which are also equivalents by this second condition, that these play the role of the other category. Right, so I've sort of split up each of these categories here into kind of two pieces, and then there's some bigger thing that encapsulates all of them. And so if I think about what this E is, well, by definition, it has a semi-orthogonal decomposition in two pieces, namely E minus and its left orthogonal, or E plus and its left orthogonal. So this means that E has a semi-orthogonal decomposition, where one piece is like, C B, and the other piece is C psi, or the other way around, depending on which way you do it. And so I can ask sort of, where it has a semi-orthogonal decomposition, where kind of the gluing functor is one of these sort of compositions of functors here. And so I can ask sort of, how do these arise in algebraic geometry? And I'd like to point out as a sort of partial answer, this theorem of Bodzenta with Will Donovan, which I think, this is a very nice result, so let Y, so suppose I have a map from Y to C mod C star, as I said before, and I told you before that like a map to C mod C star like is the same thing as picking out a divisor on Y. Picking out a divisor D on Y, then the root stack. So, okay, so in algebraic geometry, so maybe before I state the theorem, let me define this root stack. So what is the root stack of Y associated to the divisor? So this thing by definition is the pullback of something. So it has a map to Y, and Y, as we said before, has a map to C mod C star. And then C mod C star has a map to C mod C star, taking X to X squared. Right, this is the squaring map. So this is the definition of the root stack. It's something that is defined by sort of taking Y to C mod C star and pulling back along this thing. So now the point is that you have a section not of your line bundle, but of the square of your line bundle. Their theorem is that the root stack has a semi-orthogonal decomposition. Coherent sheaves on the root stack Y over D has a semi-orthogonal decomposition whose two pieces are coherent sheaves on Y and coherent sheaves on D. So maybe since this is the end of my time, I'll just say that this is kind of the punchline of this talk, is that their theorem is suggesting that like when you want to get spherical pairs, which is something that we really want to do in algebraic geometry, like these come naturally from something to do with maybe the root stack of C mod C star. And that this kind of root stack is something that like naturally has like multiple semi-orthogonal decompositions in it. And this could play a role in sort of developing these perverse Schobers in algebraic geometry. Let me just kind of say that, the way I think about this, and they have a remark to this extent in their paper, that this says that like, that the root stack, essentially, what this is saying to me is that the root stack looks like a blow up in codimension 1. In the sense that there's this famous semi-orthogonal decomposition of a blow up. If I blow up in codimension 2, a variety Y in a divisor in a codimension 2 sub variety D, then I get this semi-orthogonal decomposition, coherent sheaves on Y, coherent sheaves on D. And sort of now I'm getting this where D was a divisor, and so this is some codimension 1 version of a blow up. Maybe the punchline of this talk is that I think that this is going to play a role in sort of future developments in categorical birational geometry. So I've reached the end of my time, so I'll end there. So thanks.